going to turn our attention in section 2.3 to continuity. What does it mean for a function to be continuous? We talked a little bit in 2.1 and 2.2 about functions that were well behaved, and we said we're going to formalize that a little more later. So here's one quality of well-behaved functions. They are continuous. That means, informally, you could draw a continuous function without picking up your pencil. And what I have here are 3 examples of functions that are not continuous. You're going to write in, there's a specific kind of discontinuity for each one. So, but I want you to notice that each of these functions, if I tried to draw this, I could try to draw this function, but when I got to write about here, there's no way to skip over that hole without picking up my pencil. So there is a discontinuity. Specifically, this one we call a removable discontinuity. Here, if I were trying to draw along this function, I was drawing fine and fine and fine and fine, but then I started drawing up toward infinity. So there's no way I can jump down to this next branch without picking up my pencil to start in on this new branch. So anytime your break in your graph comes from having gone up toward positive infinity or down toward negative infinity, we call that a, you might guess, infinite discontinuity. Infinite discontinuity. This last type, you can see I would have a problem if I was trying to draw this without picking up my pencil, even if I tried to draw from the easy direction. I could draw my dot there, but when it's time to draw the other piece of my graph, I'm going to have to pick up my pencil. So here, there was no place where my graph went up toward positive or negative infinity, so it's not an infinite discontinuity, but you can see how there's a break in the graph. We call that a jump discontinuity. Jump discontinuity. So you're going to need to recognize all 3 of these types. Make sure that those 3 words are written in for you. You'll have to be able to identify them. I'm going to bring back this graph that we used when we were learning about one-sided limits, so the limit of a function from the left-hand side or from the right-hand side. And we're going to use this same picture to start to understand how we can find discontinuities in our function. So there is a formal definition for continuity, which we are building up to. But for now, what I want you to think about, if I asked you to reproduce this graph, where is it that you would have to pick up your pencil? So I noticed that if I try to draw along this graph, I have a problem here at the place where x equals 1. I got to that open circle, and then to get to the next part, I'm going to have to jump up to this part here. So I'm going to jump from here to here. I had to pick up my pencil. And here at x equals 2, there's another problem. The limit exists at the place where x equals 2, but in order to leave that hole, I'm going to have to pick up my pencil, even though it's just for like an infinitely small moment to jump over that one empty point. So I would say that this function has discontinuities at x equals 1 and x equals 2. That's here. All the rest of the function I was able to draw without lifting up my pencil. So I would say that this function is continuous everywhere else on its domain. I'll get my face out of the way so you can see. So I'm going to conclude that this function is continuous for all x on the interval 0 to 4, except at x equals 1 and x equals 2. So this function has discontinuities at x equals 1 and x equals 2. I put this other little part in here about the endpoints, just because the endpoints, they sort of have this special consideration. We said they were special when we were talking about the limits. Even though usually we have to consider the limit from both sides, if there's only one endpoint, if we're at an endpoint of the function, we don't have to consider the limit from the other side where it doesn't exist. I think it's even less of a confusing thing here for continuity. I was able to draw the function right up to the place where x equals 0 and right up to the place where x equals 4. So there's no concerns about continuity as you approach the endpoint of your interval. So here's an important idea. For those 2 points of discontinuity we talked about, x equals 1 and x equals 2, we've been asked to find f of c, the limit as x approaches c from the left and from the right of f of c, and see if we notice any patterns. So I say the limit as x approaches 1 from the left, I was headed toward that point. We'll call this f of x. So the limit as x approached 1 from the left of f of x, I was headed toward that y value, that's 0. What is the limit as x approaches 1 from the right? I would come in from here, and I was headed to that spot, a different spot, where y equals 1. So notice the limits do not match, so the limit as x approaches 1 does not exist. There's a second question here, which is what is f of 1? Well, it happens to be the place where the dot is filled in. That looks like 1. Okay, so we knew there was a discontinuity, and notice what happens here. This is where we're going to start to look. And by here, you can't see where I'm pointing. I'm actually pointing at this, what I just wrote in purple. So that's important. That's going to lead us to our formal definition of continuity. Now let's check out where x equals 2. At the place where x equals 2, I can try to find the limit. The limit as x approaches 2 from the left. This is coming in from the left. I was headed toward that blank circle, right, of f of x. It's okay if the point didn't get filled in. The limit is about where I was headed. That looks like a y value of 1. If I try to find the limit as x approaches 2 from the right of f of x, I was coming along here. I was headed for that same open circle. I have the same limit. So in this case, the limit as x approaches 2 of f of x does exist because my limit from the left was equal to the limit from the right. I have a second question here, which was, what is f of 2? Well, f of 2 is the y value of that dot that got colored in. That's 2. So pause the video and try those 3 questions down at the bottom of page 1, 3 true or false questions. And you can use this graph that we've been working with to help you find examples and counterexamples to see if you can come to some conclusions about those 3 questions. So here we go on page 2. This is our big definition for 2.3. A function is continuous. Let's not worry about the endpoints of a function. So we're just going to focus on a part of a function that's not an endpoint. Here's our formal definition. A function is continuous at an interior point of its domain if the limit as x approaches c of f of x is equal to f of c. What does this mean? This means that a function is continuous at a certain x value if the limit at that x value exists and that limit is exactly equal to the actual function value. So you probably noticed some things in those last 3 questions, and let's just notice here at x equals 2, the limit exists. Oh, I need my marker. The limit as I approach 2 from the left equaled the limit as I approach 2 from the right. So the limit existed. Yay! But notice the limit was not equal. The limit was 1, right? The limit was not equal to the actual function value. That's what made that whole. So the limit existed, but it was not equal to the actual function value. That makes a removable discontinuity. Here at x equals 1, let's see if that'll undo. At x equals 1, the limit from the left was 0. The limit from the right was 1. The limit didn't even exist, so there wasn't even a limit to check to see if it was equal to the function value. So that's your formal definition for continuity at a point.